Black holes might contain another universe, not in the movie sense, not as a tunnel you could fly through, not as a claim that astronomers have discovered a hidden cosmos behind the event horizon. I know how that sounds. It sounds like we're about to leave physics and drift into science fiction. But the strange thing is, this idea doesn't come from wild imagination first. It comes from a very sober question that physicists have wrestled with for decades, including researchers like Stephen Hawking, Juan Maldacena, and Leonard Susskind. When a black hole forms and then slowly evaporates, what happens to the information about everything that fell in? Because depending on how you answer that, you're forced to rethink what a black hole interior even is. And once you do that, the phrase "another universe inside" stops sounding like pure fantasy and starts sounding like a cautious, speculative possibility suggested by the rules of quantum mechanics and gravity. So here's the promise of this video. We're going to build the intuition step by step with no equations. We'll use thought experiments and analogies because the math is not the point today. The point is the shape of the problem. And we'll keep 3 questions open in the background, like threads we'll come back to later. First, if information can't be destroyed, where is reality keeping the books when something falls into a black hole? Second, what does inside mean if the boundary of a region might carry the full description of what's inside? Third, if black holes could hide or even generate other universes, why don't we see any evidence? Let's start by getting the meaning right, because this topic is a magnet for misunderstandings. When people say a black hole might contain another universe, they could mean several different things. They do not mean we have confirmed that real astrophysical black holes contain baby universes. We haven't. They do not mean you could fall into a black hole and safely arrive in a new universe. The physics we understand does not give us a survivable route, and even the most optimistic scenarios involve conditions that are unimaginably extreme. And they do not mean black holes are portals in the casual sense, where the universe conveniently connects distant places like a subway system. What people often mean is something more technical and more careful. They mean there are speculative models in quantum gravity where the deep interior of a black hole does not end in a literal, fatal end of physics singularity. Instead, the interior geometry could evolve into a new, expanding spacetime region that is effectively disconnected from ours. From our perspective, it looks like a black hole. From the inside, it could resemble a cosmology with its own arrow of time. That is one idea. But there's another, arguably more subtle idea that doesn't start with baby universes at all. It starts with an accounting problem. Black holes seem to force reality to store information in an unfamiliar place. And that unfamiliar place is the horizon, the boundary. That boundary-first view leads to something called the holographic principle, and it changes how we think about the inside. So before we return to black holes, we need a quick mental tool. The difference between what is fundamental and what is emergent. Think about temperature. Temperature feels like a basic property, hot or cold. But temperature is not a fundamental ingredient in the same way that, say, electric charge appears to be fundamental. Temperature is a summary. It's what you get when you stop tracking trillions of microscopic motions and you describe the system in bulk. If you zoom in far enough, temperature disappears. You just have particles moving and colliding. And yet, temperature is completely real. It predicts what happens. It controls how systems exchange energy. It's measurable. It matters. Temperature is emergent. Or take a different analogy. A map. A map is not the city. It throws away almost everything. The map does not contain the smell after rain, the noise of traffic, the texture of brick walls, or the conversations in a cafe. And yet the map is powerful because it keeps the right information for a purpose. It's a compressed description. Or consider a user interface on your phone. You drag an icon into a trash bin. It feels like you threw it away. But inside the electronics, there is no tiny trash bin. There are physical states changing in circuits, charges rearranging, memory being rewritten. The trash bin is not a lie, it's a layer. It's a way of interacting with complexity without drowning in it. Here's the key idea to carry into black holes. Emergent does not mean fake. Emergent means real, at its level, even if it's not the deepest description. And black holes are where physicists began to suspect that space and time themselves might be, at least in part, emergent descriptions, more like temperature than like a solid object. Now we can approach the black hole puzzle in the right mood, not as a story about mystical tunnels, but as a story about which description of reality is fundamental. So let's walk into the paradox. A black hole forms when matter collapses under its own gravity, compressing so much that an event horizon forms a boundary beyond which signals can't return to the outside world. Classically, black holes looked simple. For a long time, physicists thought black holes were defined by just a few macroscopic properties, mass, charge, and spin. Everything else about what fell in seemed erased from the outside. But then quantum mechanics forced a twist. In the 1970s, Stephen Hawking discovered that black holes are not perfectly black. Quantum effects near the horizon allow black holes to emit radiation now called Hawking radiation. Over an enormous amount of time, a black hole can lose mass and eventually evaporate away. And that creates a problem that is almost childlike in its simplicity. Imagine throwing an encyclopedia into a black hole. Page after page of detailed information words, diagrams, history, fingerprints on paper, all the tiny patterns that distinguish that encyclopedia from any other object. If the black hole eventually evaporates, what comes out? Hawking radiation, in its simplest description, looks thermal, random, like the radiation doesn't remember the fine details of what fell in. So it sounds as if the information about the encyclopedia is destroyed. And that is a nightmare for quantum physics. In ordinary quantum mechanics, the evolution of a closed system is, in principle, reversible. If you knew the complete quantum state at one time, you could evolve it forward or backward. Information isn't supposed to be truly deleted. If black holes delete information, then black holes don't just break a small rule. They break the framework that lets quantum theory make sense. This is the black hole information paradox. And this is where the first open question becomes urgent. If information can't be destroyed, where is it? Because if it's not in the outgoing radiation in any recoverable way, and it's not accessible outside, and the black hole is gone, then where did it go? This is not just philosophy. It's a demand for consistency between quantum mechanics and gravity. Now comes the clue that changed everything. Black holes behave like thermodynamic objects. They have a temperature, they radiate, and they have an entropy. Entropy is often described as disorder, but a better intuition is entropy counts how many microscopic ways a system could be arranged while still looking the same at a macroscopic level. If you have a deck of cards, there are many more shuffled configurations than ordered ones. Entropy is about multiplicity of hidden possibilities. For ordinary matter, entropy tends to scale with volume. Bigger box, more possible arrangements. So you would expect that if we could pack information into a region, the maximum amount of information you could store would scale with the volume of that region. But black holes do something astonishing. The entropy of a black hole scales with the area of its event horizon. Area, not volume. Let that sink in. It's as if the maximum information content of a region of space is not proportional to how much room is inside, but proportional to the size of the boundary. That is a radical hint about how spacetime stores information. Imagine you have a sphere in space. If you believe the interior volume was what mattered, you'd think you could store information throughout the whole interior, like stuffing a warehouse. But black hole entropy whispers something else. The fundamental bookkeeping may live on the surface, like all the degrees of freedom that truly count scale like pixels on a screen, not like atoms in a room. This is where the holographic principle enters. A hologram, in the everyday sense, is a 2D surface that encodes a 3D image. The surface is not the 3D object, but it contains a pattern that can reconstruct the object's appearance. The holographic principle, in physics, is the idea that a region of space can be fully described by degrees of freedom on its boundary. Important clarification. This does not mean the world is an illusion. It does not mean we are literally a projection in a cartoon way. It means that the deepest description might organize information differently than our spatial intuition suggests. Instead of the interior contains the information, it could be that the boundary encodes the interior. Now, if you're feeling a little uneasy, that's the correct response, because this collides with how we naturally think. We think a thing is inside a box because it's inside the box. We think the information about a room is in the room. But black holes are telling us that when gravity and quantum mechanics both matter, the universe might not store information the way a box stores objects. And that brings us to the second open question. What does inside even mean if the boundary can encode the whole story? If the full description of what happens in the volume can be written on the boundary, then perhaps the inside is not a fundamental container. Perhaps it is a derived concept, an emergent space that is reconstructed from boundary information. This sounds abstract, so let's ground it with a simple thought experiment. Imagine you are not allowed to look inside a sealed room. You can only measure things on its walls, tiny vibrations, thermal fluctuations, electromagnetic fields, and so on. In everyday life, that wouldn't give you a perfect reconstruction. But in principle, if the laws of physics allow it, and if you have complete access to the right variables, the boundary data could be enough to infer the interior. In some modern approaches to quantum gravity, that's not just possible. It's the point. The interior is not stored inside, it's encoded in patterns of information that can be associated with a boundary. Now we need to be careful. The holographic principle is a broad idea, but physicists want more than poetry. They want at least one clean setting where it becomes precise. That's where ADS/CFT comes in. ADS/CFT is a duality discovered in the late 1990s and developed by many researchers. The names stand for anti-de Sitter space and conformal field theory. Here's the intuition first picture. Anti-de Sitter space, or ADES, is a kind of spacetime with a particular curvature. It is not the same as our observed universe, which appears to be expanding in a way closer to a de Sitter-like spacetime. That distinction matters, and we'll come back to it. In ADS/CFT, a gravitational theory in the bulk inside the volume can be equivalent to a quantum theory without gravity living on the boundary of that spacetime. Equivalent, not similar, not approximately related. In the idealized model, they are two languages describing the same underlying physics. One language talks about geometry, gravity, black holes in the bulk. The other language talks about quantum fields on the boundary. And somehow the boundary theory can encode everything that happens in the bulk. That's a stunning proof of concept for holography. Now, a crucial limitation, ADS/CFT, is not a confirmed description of our real universe. It's a powerful theoretical laboratory. It's the clearest case where we know holography can work. But extending this kind of duality to the cosmos we actually inhabit is an active research frontier, not a settled result. So we should not say, ADS/AFT proves our universe is a hologram. What we can say is ADS/AFT shows that the holographic idea can be mathematically consistent and extraordinarily precise in at least one broad class of spacetimes. And that matters because it tells us the black hole area law and the holographic principle are not just philosophical speculations, they point toward real structure. Now let's bring ADS/CFT back to black holes. In many holographic setups, black holes in the bulk correspond to certain thermal, highly entangled states in the boundary theory, which means something profound. What looks like a hidden interior region behind a horizon can have a complete description in a theory that lives outside on a boundary without ever needing to refer to an inside in the same way. This doesn't automatically solve every puzzle, but it changes what a solution could look like, because now the first open question, where is information kept, has a plausible direction. The information is not necessarily destroyed. It can remain encoded in correlations, in entanglement, in subtle patterns that are not visible to a coarse observer, but are present in the full quantum description. In other words, the universe may keep the books on the boundary, And now we're ready to connect this back to the title. Why would this suggest another universe inside a black hole? Because once you treat the interior as emergent, you open the door to a new kind of possibility. Different emergent spacetimes could be reconstructed from the same underlying information, depending on how the degrees of freedom are organized and which observers have access to which descriptions. And separately, in some speculative models, the interior geometry might evolve into a new expanding region that is causally disconnected from the outside, effectively a new universe. Let's slow down and separate what is established from what is speculative. Established, or at least strongly supported by mainstream theoretical work, black holes have entropy proportional to area. Quantum effects imply Hawking radiation, and the tension between information preservation and evaporation is real. Many modern developments suggest information is preserved, though the complete story is subtle and still researched. Speculative. What exactly replaces the singularity? Whether an evaporating black hole's interior is best thought of as a separate universe, whether black holes literally give birth to baby universes, and whether our own Big Bang could be the interior of a black hole in some parent universe. So when people say black holes might contain another universe, they are stepping into the speculative zone. But they are not stepping into pure fantasy. They are responding to pressure from the established zone. Now let's make the baby universe idea intuitive without pretending it's confirmed. In classical general relativity, if you fall into a black hole, your future points toward the singularity. The singularity is not just a place, it's a breakdown of the theory's ability to describe spacetime. Densities and curvatures blow up. Physicists don't generally believe that singularities are the final word. They are more like warning signs that we used an incomplete theory outside its domain. Quantum gravity, whatever its final form, should modify what happens at extreme curvatures, and that creates an opening. One speculative possibility is that instead of ending at a singularity, the interior undergoes a kind of bounce or transitions into a new expanding region. The collapsing matter becomes, from the inside, something like the beginning of a new cosmological expansion. From the outside, you still have a black hole, a horizon, an object you can orbit, an accretion disk, gravitational waves when it merges. From the inside, the geometry could be completely different, with its own large-scale expansion. That's the rough intuition behind baby universe scenarios. Now here's a subtle but important point. Even if such an interior expansion happened, it would not necessarily be accessible from our universe. The horizon is a one-way boundary. Causal structure matters, so the baby universe, if it exists, could be causally disconnected from the parent universe. It would be inside in a geometric sense, but not inside in the sense of being reachable or communicable. At this point, you might ask, isn't that just relabeling? If we can never interact with it, what does it mean to say it exists? That question isn't a distraction, it's central, because it forces us to talk about what real means in physics. A black hole interior is already a region where ordinary intuition fails. You cannot send a signal back out. You cannot verify interior events from the outside. You infer the existence of the interior because the theory describes it, and because the external behavior seems to demand it. So the question becomes, if the best consistent theory of quantum gravity says that an evaporating black hole's interior corresponds to a new spacetime region, do we call that a real universe? Many physicists would say if it has consistent physical laws, consistent causal structure, and in principle could contain observers and events, then it's physically meaningful to call it real within that theory, whether or not we can exchange messages with it. But again, this is where we stay humble. These are ideas at the edge of what we can confidently claim. Now let's revisit the second open question. What does inside mean? Because this is where holography changes the interpretation. If the holographic principle is broadly correct, then the degrees of freedom that describe a region might be associated with its boundary. So the interior might be like a reconstructed 3D picture from a 2D encoding. In that framing, talking about a baby universe inside a black hole might be like talking about a 3D scene encoded on a surface. The scene can be rich, self-consistent, and large. But its fundamental description might not be located inside in the naive way. This can feel like word games until you notice how it solves a practical problem. The information paradox wants information to be preserved. The area law suggests information capacity scales with boundary area. Holography suggests boundary encoding is natural, and ADS-CFT suggests this can be literal equivalence in the right settings. So one coherent picture is black hole evaporation does not destroy information. Information is preserved in the full quantum description, and what we call the interior is an emergent encoded story that does not violate quantum mechanics. That picture doesn't require baby universes, but it makes baby universes less absurd, because it already loosens the grip of naive interior space. Now we can connect to a deeper idea that has become increasingly prominent in modern theoretical physics. Space-time itself may emerge from quantum entanglement. Entanglement is a kind of correlation that is stronger than classical correlation. It is not just we don't know which outcome yet. It's a structural feature of the joint quantum state. In some research programs, the pattern of entanglement between degrees of freedom is what gives rise to the geometry of space. Roughly speaking, change the entanglement structure, and you change the connectivity and shape of emergent space. If that's even partly true, then geometry is not the bedrock. Geometry is a kind of large-scale summary of underlying quantum information relationships, and that returns us to our earlier analogy. Temperature is real, but not fundamental. It emerges from microscopic motion. Similarly, an interior spacetime could be real but not fundamental. It could emerge from microscopic quantum information. So when we say a black hole might contain another universe, one interpretation becomes a black hole might correspond to an underlying quantum state whose emergent description includes an interior region that behaves like an expanding cosmos. Again, speculative. But now it has a home inside a broader motivated view of emergence. Now let's address the third open question. If any of this is plausible, why don't we see evidence? Part of the answer is almost too obvious, but it's worth saying anyway. A horizon is designed by the causal structure of spacetime to prevent information from coming back out in the classical sense. The interior is not visible to outside observers. That's what makes a black hole a black hole. So if a baby universe existed behind the horizon, we should not expect to see a postcard from it. But you might still hope for indirect signs. For example, maybe black holes would violate some conservation law or show anomalies. The trouble is, the external behavior of a black hole is governed by a small set of properties, and the horizon hides the details. Many different interior stories could lead to very similar exterior observations. This is why the debate becomes so theoretical. Our direct experimental access is limited. However, the information problem is one area where theory itself acts like a constraint. You can't just invent any interior you want. It has to be consistent with quantum mechanics and thermodynamics and whatever the full theory of gravity is. So in practice, the evidence today is not a telescope image of a baby universe. It's the way different frameworks either do or don't allow a consistent accounting of information. This is also why ADS-CFT is so important. It's a case where the accounting is explicit. The boundary theory is unitary, meaning it preserves information. And if the bulk theory is equivalent to it, then the bulk should preserve information too. In that laboratory, black holes can't be information shredders in the fundamental description. Now, does that directly prove what happens in real astrophysical black holes? Not directly. Our universe is not exactly ADS, and we don't have a complete non-perturbative quantum gravity description of the universe we live in. But as a clue, it's powerful. It suggests that if we ever do have a full theory, it will likely preserve information, and it will likely treat horizons and boundaries as central to the bookkeeping. Now we're ready to assemble the full ladder of ideas in one clean arc. First, quantum mechanics teaches us that information is not supposed to be destroyed in fundamental evolution. Second, black holes with Hawking evaporation seem to threaten that principle. Third, black hole thermodynamics tells us black holes have entropy. Fourth, that entropy scales with area, not volume. Fifth, area scaling hints that the information content of a region is encoded on its boundary. Sixth, the holographic principle takes that hint seriously. Seventh, ADSACFT provides a proof of concept that boundary encoding can be exact, at least in certain spacetimes. Eighth, this pushes us toward emergence. Space-time geometry, including black hole interiors, might be derived descriptions from quantum information. And ninth, once interior becomes a derived concept, the possibility of another universe inside becomes less like a wild add-on and more like a speculative branch consistent with the overall direction of the theory. Now, what does this mean for our biggest origin story, the Big Bang? Here we have to be careful again. It is tempting to say, maybe our universe is inside a black hole. This idea has been explored in various forms, and it's compelling in a certain poetic way. Black holes are regions of space-time with horizons. Our observable universe also has horizon-like features, limits to what we can see, cosmic event horizons due to expansion. But poetic resemblance is not proof. Still, the baby universe picture gives a provocative reframing. If black holes can create new expanding regions, then perhaps the Big Bang is not the beginning of everything. Perhaps it's the beginning of our branch of space-time. And before the Big Bang might not be a time in our universe at all, but something more like a parent structure from which our region emerged. That would not necessarily answer every question. It would shift them. Instead of asking, what happened before time began? We might ask, what physical process produced this space-time region, and how is it connected to a larger structure? Now, do we have evidence for that? No, not at present. But black holes give us something rare. They force us to ask questions about the global structure of space-time in a way that is mathematically unavoidable, because they bring quantum mechanics and gravity into conflict, and that conflict doesn't let us keep our comfortable intuitions. Now let's return to the phrase another universe because it can mean two different things, and separating them makes us more honest, meaning one, a literal, geometrically separate expanding space-time region, disconnected from ours. That's the baby universe scenario. It's highly speculative. It depends on what resolves the singularity and on how quantum gravity behaves in the deepest interior. Meaning two, an emergent interior description that, from the point of view of effective physics, behaves like a self-contained world, with its own arrow of time and large-scale structure, even if fundamentally it's encoded in boundary degrees of freedom. This is still not fully established, but it is aligned with holographic ideas and with the broader trend of thinking about space-time as emergent. In both cases, the message is not black holes are magical. The message is, our classical picture of space as a container may be the wrong mental model at the deepest level. And that brings us to a final, quiet point one that matters even if baby universes turn out to be wrong. If space-time is emergent, then many things we treat as fundamental might be like temperature, not illusions, not mistakes, but summaries of deeper rules. That is not a downgrade of reality, it's a refinement. A rainbow is emergent from droplets and light, but it's still real enough to inspire paintings, guide sailors, and be measured by instruments. A hurricane is emergent from molecules of air and ocean heat, but it's real enough to reshape coastlines, so if a black hole interior is emergent, it can still be as real as anything we ever experience real at the level where observers, clocks, and galaxies exist. And that, in some sense, is the core emotional shock of modern theoretical physics. Reality may be layered. Now, let's close our three questions explicitly. First, where is reality keeping the books when something falls into a black hole? The best supported direction is that information is not destroyed. In many modern frameworks, the bookkeeping is tied to the horizon and to subtle quantum correlations. Exactly how that appears in our universe is still researched, but the overall trend strongly favors information preservation. Second, what does inside mean? It may mean an effective emergent description reconstructed from boundary-encoded information, rather than an independently fundamental region containing its own degrees of freedom in the naive way. The interior can be meaningful and consistent while still being derived in the deepest description. Third, if black holes could contain or generate other universes, why don't we see evidence? Because horizons limit access by design, and because many different interior stories can look almost identical from the outside. Our best constraints come not from direct observation of the interior, but from demanding consistency between quantum theory, thermodynamics, and gravity. So where does that leave the title? Why black holes might contain another universe is not a statement of fact. It's a statement of pressure. The pressure comes from the information paradox. The pressure comes from entropy scaling with area. The pressure comes from holography and from proof-of-concept dualities like ADS/CFT, even though our universe is not exactly the same setting. And under that pressure, the black hole stops being a simple object with a hidden interior and starts being a boundary-centered system where space, time, and inside might be emergent concepts. In that new view, the idea of a baby universe is still speculative, but it's no longer random. It's one of the ways the universe might remain consistent with itself. If you want more long-form physics documentaries like This Calm Intuition First, No Equations, consider subscribing. And I'll leave you with one question, because it's the kind of question that sits at the edge of physics and philosophy in a productive way. If a black hole's interior can be a self-consistent world, but the most fundamental description lives on a boundary we can never see directly, what should we count as real?